So now we start the question number 4. I have written few parts of the question 4 and I just explained from the given solution. So we are given that r is equal to xi plus yj plus zk, and we were looking for the gradient operator applied on one of r magnitude. This was the part A. So r magnitude for this given vector is x square plus y square plus z square. And because this time we are in 3 dimension, so gradient operator will be partial by partial xi plus partial by partial yj and plus partial by partial z, the kth component, and this is the value of this 1 over r magnitude. This can be moved in the numerator and power becomes negative 1 by 2, and now I apply the derivative with respect to this x, but still there will be I component, j component, k component. I mean the answer should be a vector. So let's take the derivative of this one. So we can apply the chain rule. This negative 1 by 2 will come in the start. I will subtract 1 from the exponent. Then by using the chain rule, I multiply with the derivative of the inner function with respect to x. That will be 2x. The derivative of y square and z square when taken with respect to x, it will be 0. This will be I over here. Similarly, I calculated the other derivatives. I simplified, and this was taken out as a common, and ultimately we achieved this form. The question 4 part B is asking for k dot, the gradient operator applied on this 1 over r magnitude, which we have already calculated in the part A. This is the answer of that expression from the part A. Now we are going to take the dot product of two vectors. So the first expression, this k unit vector, can be written as 0i plus 0j plus 1k, and here I moved this expression with every component. This is negative x over the same expression I, then y component, and then z component. So when we take the dot product, each component is multiplied and the unit vectors are vanished because the dot product is a scalar number. So 0 times this expression will be 0, and from here 0 times this expression will be 0, and this 1 time negative z, it will be negative z over x square plus y square plus z square to power 3 by 2. So this is the simplified expression. So in the C part, they asked to find the gradient operator applied on this k dot delta 1 over r magnitude, which we have already calculated in B part. So let's write the answer for that. Now we are going to apply the derivative or this gradient operator on over here, which is partial by partial xi plus partial by partial yj plus partial by partial zk applied on negative z. I have just moved this in the numerator. Now we are going to simplify it. The derivative with respect to x. So when I will be taking derivative with respect to x, this negative z is just a constant. There will be no effect of the derivative with respect to x on this one. And we apply the chain rule for the derivative of this expression. For that negative 3 by 2 will come the start, x square plus y square plus z square, and 1 will be subtracted from the exponent. It will be negative 5 by 2, and then we multiply with the derivative of the inner function with respect to x. That will be 2x, and by the way, this negative z have been already moved out, plus 0, and there will be I component. And likewise, I calculated the derivative of the second expression. I am writing the answer directly. That will be negative z x square plus y square plus z square to power negative 5 by 2 into 2y, the j component. But when we apply the derivative on the third vector, because this is the derivative with respect to z, and here we have z in the first expression and the z in the second expression, so it means the product rule will be applied. First of all, I move this negative outside, and we apply the product rule of the derivative on this expression from z to this. So z will remain as it is. No, let's take the derivative of z with respect to z. It will be 1. The second expression will be rewritten as it is, power negative 3 by 2. Then plus z will remain as it is. The derivative of the other function, this expression with respect to z, it will be that negative 3 by 2 will come in the start, and x square plus y square plus z square to power negative 5 by 2, and the derivative of the inner function with respect to z will be 2z This will be the k component. So now we simplify every component. From here this 2 will be cancelled with this 2. Here we have x from here and z from here, but here is negative and here is negative, that will become positive. So on simplification we get 3 times this is x and z, so 3 times xz divided by x square plus y square plus z square to power positive 5 by 2, and this is the I component. Likewise here we have yes, so I missed one expression over here when I was taking the derivative of the second expression with respect to y. It should be negative 3 by 2 over here as well, because that power will come in the start. So this 2 will be cancelled with this 2, and this negative negative positive, it will become positive 3yz divided by x square plus y square plus z square to power 5 by 2, and this is the j component. And now we simplify the last component. So if I take a positive here and I just move this negative inside, it will become negative 1 over x square plus y square plus z square to power positive 3 by 2, and then this 2 is cancelled with the 2 and it is negative 3z, and 2 from here 2 is already cancelled, so negative 3z square, but this is negative outside there, so that will make it positive 3z square, and divided by it will be x square plus y square plus z square to power positive 5 by 2, and this is the k component. Now we further simplify this last expression of the k component, but first two expressions will remain as it is, 3xz over x square plus y square plus z square to power 5 by 2 I component plus 3yz divided by x square plus y square plus z square to power 5 by 2 j component. And the last one, if I make the denominator same, I mean this is power 5 by 2 and this is power 3 by 2. If this is multiplied with x square plus y square plus z square to power 1, this will also become x square plus y square plus z square to power 5 by 2, and over here it will become x square plus y square plus z square. So by making the denominator same, in the denominator I will have x square plus y square plus z square to power 5 by 2, because I multiplied with x square plus y square plus z square here in the denominator. Same will go in the numerator, and there is a negative. I'm doing it directly, so it will become negative x square, negative y square, negative z square, and we have already that for plus 3z square, and this is the k component. But if I simplify it further, so this will be 2z square minus x square minus y square. Okay, now we take whatever we can take common, so we can take basically this expression in the denominator as a common. It's 1 over x square plus y square plus z square to power 5 by 2, and here we will have 3xzi plus 3yzj and plus 2z square minus x square minus y square k component. And this is the answer of this part. In the part 4 we are looking for the solution of this part, and this was already calculated in part A. So this will be k unit vector cross product, and the answer of this was let's just write that it was negative 1 over x square plus y square plus z square to power 3 by 2, and here we had xi plus yj plus zk. So because we are taking the cross product of two vectors, and this number is just a scalar, so that can be taken outside the cross product, so it will be negative 1 over x square plus y square plus z square to power 3 by 2, and we have to take the cross product of this k cross xi plus yj plus zk. So let's take the cross product of the factors. It will be negative 1 over x square plus y square plus z square. And when we multiply, okay, there are different ways to take the cross product, but one of them we directly multiply. So here is the k component. When it multiplied with x will remain as it is. So k vector will have cross product with the vector I, then plus y. K vector will have a cross product with j plus z. K vector will have a cross product with the k itself. And here we have a rule for the cross product, we can remember. So let's say here is I, here is j, and here is k. But the cross product of vector k with itself is 0, so this expression will become 0. Here it is k cross j, so k goes back from to j, so it will be negative I because we are going in the backward direction. On the other hand, it is k cross I, that's going in the forward direction, so k cross I will give us j. So this will be negative 1 over x square plus y square plus z square to power, this was 3 by 2. So this will be x, because this k cross I is just j, so there will be j. And then we have k cross j, which we already said that it will be plus y, and this will be I because k cross j is going backward direction, so it will be negative I. Let's simplify it further. This will be okay, let's write the I component first. So it will become y over x square plus y square plus z square to power 3 by 2 I, and then negative x over x square plus y square plus z square to power 3 by 2, and this will be the k component. This is the answer of question 4 part D. Now we start the part E. Here we are looking the cross product of this gradient vector with this vector, which we have already calculated in part D. So let's write them. So this gradient vector is basically partial by partial xi plus partial by partial yj plus partial by partial zk, and we have to take its cross product with this vector which we already calculated, and we can write that vector is y over x square plus y square plus z square to power 3 by 2 I minus x over x square plus y square plus z square to power 3 by 2 j. So now we take the cross product, although we can use a determinant method, but I am going to apply direct method. I start with this partial by partial xi and multiply with both of them in the first line, this one in the second line, and this one in the third line. So it will become partial by partial x y. For simplicity, I am moving this in the numerator, so this will become y times x square plus y square plus z square to power negative 3 by 2, and here I will have I cross I. Then this will become minus the second one. Again I have to apply partial by partial x on x times x square plus y square plus z square to power negative 3 by 2, and this time it is I from here and j from here, so it will be I cross j. Then we start with the second one, partial by partial y, and apply on both of the expression. So it will be partial by partial y on y times x square plus y square plus z square to power negative 3 by 2, and this will be okay. Here we have j and here we have I, so this will be j cross I. Then plus minus minus, we have partial by partial y applied on the expression of x square plus y square plus z square to power negative 3 by 2, and from here we had j, and this is also j, so this will be j cross j. And in the last line we start with this partial by partial z, so partial by partial z applied on y times the first one x square plus y square plus z square to power negative 3 by 2, and this will be Here we have k and here we have a I, so this will be k cross I, and it will be negative partial z applied on x into x square plus y square plus z square to power negative 3 by 2, and it will be k cross j. Now we calculate each partial derivative. So but for the first one, you can notice this is I cross I, the cross product of vector itself is 0, so this whole expression becomes 0. Similarly, this whole expression also becomes 0. Now I am going to calculate the partial derivative of this one, so this negative remains over there. Let's take the derivative of this expression with respect to x, but this can be noted that both expressions contain x, so we have to apply the product rule. So if I take the derivative with respect to x of the first one, it will be 1. The second expression remains as it is, negative 3 by 2, plus then x will be as it is the derivative of this second expression by using the same chain rule as we did earlier. It will become negative 3 by 2 into x square plus y square plus z square to power negative 5 by 2. And because we are calculating with respect to x, so the derivative of the inner function with respect to x will be 2x. And then outside we have I cross j. So I cross j will be basically vector k. Now let's go to the second line. For the second line, this expression is already 0, so we are calculating the derivative for this one. And this time the derivative is with respect to y, and the y is over here and also over here, so we have to apply the product rule. So the derivative of first y is 1 and second one will be x square plus y square plus z square to power negative 3 by 2, plus then first y will be written as it is. The derivative of this expression with respect to y, we have to apply the chain rule, which will be negative 3 by 2 x square plus y square plus z square to power negative 5 by 2, and then it will be 2y. And outside the whole expression we have this j cross I, so it will be basically negative k because they are going in the clockwise direction. You can see from that diagram I made. And in the last one, let's take the derivative of these derivatives. So partial by partial z, you can notice this y is independent of z, so that y will come outside, and the derivative will be applied only this expression, but by using the chain rule, so it will be negative 3 by 2 into x square plus y square plus z square to power negative 5 by 2, and the derivative of the inner function with respect to z will be 2z, and here we have k cross I, that will be j. And after that I have negative. Now let's take the derivative of this expression with respect to z. This x is also a constant with respect to z, so it will come outside, and we have to apply the derivative of this expression with respect to z, so it will be negative 3 by 2 into x square plus y square plus z square to power negative 5 by 2, and it will be 2z, and this k cross j will be negative I. Now let's simplify every expression. Let's start with the very first expression, so that will become negative 1 over x square plus y square plus z square to power positive 3 by 2, and that is the k component because k was already there. And the second one, we can notice that this 2 is cancelled with the 2. From here I have x, and from here I have x, that will become x square, so this is negative 3x square, but there was negative in the beginning, that will be positive 3x square divided by, it will be x square plus y square plus z square to power positive 5 by 2, and this is also a k component. Now we go in the second line. So here we have x square plus y square plus z square to power negative 3 by 2, and there is a negative case, so it will become negative 1 over x square plus y square plus z square to power 3 by 2 and the k component. And from here we cancel this 2 with the 2, negative 3 times y, and y from here negative 3y square, but this negative will make it positive 3y square divided by that x square plus y square plus z square to power 5 by 2, and there is a k component. And lastly we write this j and I component. So this 2 is cancelled with the 2. Here we have negative 3 by 2, negative 3, and here we have z, this is y, so this will be negative 3yz divided by x square plus y square plus z square to power 5 by 2, and that will be the j component. And from here we have this negative and this negative positive, and this is negative, so it will be negative eventually. And then this 2 is cancelled with this 2, so z times x, it will be xz 3xz, but it will be negative 3xz divided by x square plus y square plus z square to power 5 by 2, and there is I component. Okay, let's combine the components. So first of all we have I component, which is negative 3xz divided by x square plus y square plus z square to power 5 by 2 I component, then negative 3yz divided by x square plus y square plus z square to power 5 by 2, the j component. And lastly we combine all of the k components. These two are similar and these two are similar, so if I combine them I will get negative 2 divided by x square plus y square plus z square to power positive 3 by 2 plus that will become 3x square plus 3y square divided by x square plus y square plus z square to power 5 by 2, and there is k component. But this expression can be further simplified. I'm just going to simplify this expression over here, then I will write with combining with that. So if I multiply in the denominator with x square plus y square plus z square, it will also become 5 by 2, and it's also 5 by 2 over here, so it will make 5 by that equal denominator, which will be x square plus y square plus z square to power 5 by 2, and that negative 2 will be multiplied with that multiplied expression, so it will become negative 2x square negative 2y square negative 2z square plus 3x square plus 3y square, and this is the k component. Now let's write the more simplified expression for whole of the thing. This is negative 3xz divided by x square plus y square plus z square to power 5 by 2 I component, negative 3yz divided by this x square plus y square plus z square to power 5 by 2, the j component. And this one when simplified is basically okay, so it will become x square plus y square and negative 2z square divided by x square plus y square plus z square to power 5 by 2, and this is the k component. So this is the thing which we can take factor out. So if we factor out, this will become 1 over x square plus y square, or I can take negative as a factor out as well, so negative 1 over x square plus y square plus z square to power positive 5 by 2. So we will be left with, because we have taken negative as a common, first one will be 3xzi plus 3yzj, and last one will be negative x square plus y square minus 2z square and k component. So we are done with the part E. Now we do the last part of this question 4, which is that we have to check the delta cross this k unit vector cross delta 1 over r magnitude plus the expression delta into k dot delta of 1 over r magnitude, and we have to prove this is equal to 0. This is the thing we have just calculated in the E part, and this was calculated in C part. So I'm going to plug the values and we check if this is 0. I have just plugged the values and you can notice that they are almost look like same. I mean, this negative is over here and this whole expression is exactly the same, but only difference is over here, but we can make them same. If I just take negative common from here, so it will become, so we can just do that. If I take negative common, so actually if I move that negative inside, so that will become positive, so it will become 2z square from the previous expression. I mean, basically I'm just multiplying this negative inside and it will become positive here. This negative 2z square will become positive 2z square, and the other expression will become negative x square and negative y square. Now you can notice that this everything in the bracket is exactly same. This expression and this expression is same, but there is a negative here and this is positive here, so it means they are just cancelled out. So this is equal to 0. That's it. We have proved this.